material, these two powders differ in the specific surface area, or calcination temperature if you want me. Consequently, one material, the B is higher surface area material that will start sintering, densifying about 100 degrees C lower temperature than the other one. At that time, E, I think, still stands for experimental grade. You know, I was trying, B is binder, and E, you know, at the beginning that was, it contains a very small amount of alumina, that material. It's now medical grade, in contrast to the standard grade stuff. And we did the work, we took the both materials, and we pressed them into pellets, and then we sintered them 1400 degrees, 50, 1450, 1500, and 1550. And you can clearly see that there is no difference in the grain size. And when we also measure that, we confirm there is no difference. You can take either of these two materials, and if you sinter it at that temperature, that won't be a big difference, okay? Sometimes it was confusing, you know, what was done what. Let's have a look on the aging. Aging, that's nothing new. In fact, that was a very disappointing news in the time where engineering ceramics for high temperature was developed, when it was discovered that once exposed to an aqueous environment, this yttria partially stabilized material will start transforming spontaneously at slightly elevated temperatures, and water or water vapor is necessary to foster that. And it was also found that the grain size has a significant influence on that behavior. Ever since, there were many theories, you know. I'll not go into details. Here I have the recent one I showed you. The Schubert made it on a napkin for me. No. There are half a dozen of theories. All of them are in a way correct, but none of them is generally applicable, you know, will cover everything. So we have several influences, not only one. It's not that simple as people sometimes think. Oh, aging mechanism. Okay, that's the schematic drawn by Chevalier. Actually, it's not a mechanism, it's just a version how we figure that out. Somewhere under the influence of water, some grains will decide that they find uncomfortable in this metastable state tetragonal form, and they will start transforming into the monoclinic, and that starts on the surface. Since the volume of the cell is bigger of the monoclinic stuff, you will have here a small uplift, and since the material will exert some stresses on the neighboring grains, it makes like a loose structure, and that goes deeper and deeper. Later on, people have discovered it's more complicated, and I'm afraid it's even more complicated because we have these phase separations. We never know what's where. And the monoclinic will twin, because if the volume is getting bigger, then the material wants to accommodate. So and it does it by twinning, and that will lead to a texture. The microcrack will not be statistically or randomly oriented, but they have a preferential orientation along the surface, basically. What you will see also, but from the X-rays. Okay, some on the kinetics, the lower the yttria content, the lower the yttria content, the higher will be the transformability, and the higher the temperature, the faster the transformation will occur. And we have checked this at that time. There were standard grade materials and the one with alumina added, and there is an enormous difference. So 0.25% of alumina addition indeed strongly reduces the rate of the transformation rate. We checked various atmosphere environments, but there was not such a big difference in that. Okay, and that's the well-known relationship between the in vivo and in vitro orthopedic zirconia femoral heads. But one has to be aware that this material was isostatically hot pressed and mirror polished. So the material is fine grained, it behaves different, and also the surface is much it's polished in contrast to a rough surface what you have in a dental lab. And that's why Jérôme he pointed out in his paper, for each zirconia and for each clinical application this relationship has to be established, but usually people just remember that 1 or 2 hours in vitro will give you 8 years in vivo, and that's it. So, and perhaps they even quote this Avrami, just what, and that's it. Anyway, so we were interested in whether we can also establish this kind of relationship. So let's go first the effects of the mechanical surface treatment, the effect of aging, and we'll go through the results. These were the very first results. The materials here are the standard grade. At that time, you know, E stood for experimental grade, and now I have corrected the grain size values. We have measured the equivalent diameter, but now in the standard it says the intercept, you just cut the microstructure by a line, and that makes a difference. So you'll see that the finer grained materials generally, so B and BE, will typically have higher strength than SBE with a bigger grain size, same here, but lower fracture toughness. So the material that has finer grains will have a higher inherent strength but lower fracture toughness. And to give you an impression on the grain sizes. So we applied dental grinding, different grid size, water cooling, not dry, and also sandblasting. I didn't know what kind of sandblaster is used. I asked the PhD student, a dentist, what is used. He said somewhere he found 110 micrometers, 4 bars pressure, and he used a large distance, 40 millimeters. That's quite a large distance. So that's how we generate the mechanical surface treatment. And there was nothing at that time but this ISO standard for checking the chemical stability of the material by refluxing, and we used that. And afterwards, we also, when we did mechanical fatigue testing, we went up to 1 million cycles, 15 hertz, 50 to 850 newtons, which will correspond roughly to, let's say, maximum 620 megapascal. That would be roughly about 60% of average strength of the control group. And if we check the surface, you see the ground surface anyway, in any case was heavily damaged, in part plastically deformed. You won't be surprised to see sparks. It must be very high temperatures, and also this one, the sandblasted material was also heavily damaged, perhaps less plastically deformed than that one. So it's on the surface. It's perhaps not the transformed monoclinic, but it looks like. So you get at least to have an impression. Perhaps one grain would be transformed in this material. X-ray. I'm sure I'm bothering you, but the X-ray pattern will change quite dramatically from the material. Initial material with a very sharp peak and two peaks here. Then we start seeing this one, which is the monoclinic after grinding or sandblasting. This one will get distorted. It will shift, and this is again something ignored in the aging story. And the intensity of these two peaks will be reversed. Anyway, enough to think about it. It's not just, damage and plastical deformation. So we check the amount of the monoclinic content by X or D. There was practically nothing here in the ground specimens, and the reason is the temperatures locally are much higher above the transformation temperature. The stuff transforms and it retransforms back. But in the case of sandblasted materials, we have measured about 15% of the monoclinic. At that time, I had no idea. I said, let's check both operations in the sequence. It turned out, perhaps somebody will get an idea, the monoclinic and also the properties afterwards will depend on that mechanical treatment which will be done last. If you do first grinding and then sandblasting, you'll get this one. If you do sandblasting and then after grinding, you'll get closer to the ground material. And there was a strong influence on strength. The finer grained material was more sensitive to grinding, especially than the coarser grained material, because the fracture toughness was lower, and the burr grit and water spray had an influence, but not so very pronounced one. But sandblasting created a surface compressive zone that make the material stronger afterwards under static loading. We tested 10 specimens that were not very coarse, very damaged after pressing, So what we discovered, grinding will reduce the Weibull modulus, which means will increase the variability in the strength values. You have a large scatter of values. If you do sandblasting, we also got some reduction in that. It may be because we only have 10 specimens in a group, it's not enough, and also we had pretty nice and smooth surface. But anyway, the influence of sandblasting on zirconia can be discussed. Don't take it for as a concrete this result. Okay, few fractographic pictures.